I made a small change in the title, but the content effectively remains the same. So, Professor Tangaraj in his, the first talk of today mentioned that he felt himself an interloper in a meeting dominated by archaeologists. Well, I come from the Institute of Mathematical Sciences and probably feel myself more of an interloper. Usually, and as it happened in yesterday's dinner, like when I said I was from the Institute of Mathematical Sciences, very often there would be an embarrassed silence at the other end, and the usual response would be, I was very bad with numbers in school. And then, when I say, well, I do work on, something related to Indus, I'm just not here as a tourist. The next question would be, okay, so what does it say? Well, the thing is that, actually we are trying to address something even more basic than simply deciphering it. So we are just asking, something as simple as this. How can you tell that the picture on the left is writing and the picture on the right is not? So for those of you who haven't guessed this, the picture on the left is actually a cuneiform tablet, and the picture on the right is actually just a naan, right? It just happens to, because of the heating process, haven't gotten those grooves like that. Now you might say that, this is obvious, right? Everybody knows the picture on the left is writing. Well, before it was deciphered by Rawlinson and others somewhere in the middle of 19th century, there were serious suggestions that these cuneiform tablets are actually just impressions made by, let's say, a bird walking on mud, which just happened to be accidentally baked solid. Okay? And it does look like, just bird feet, right? I mean, someone just walking across mud flats. I mean, it just happens to be very regular, though. And this is impression, or this is something that you see across many ancient languages, which prior to the decipherment, there would be very serious suggestions, this is not writing. If you look at the history of the decipherment of Mayan hieroglyphs, the dominant view in the beginning of the 20th century, led by Eric Thompson and others, was that it's too beautiful to be writing. It must be some decorative element. And when Norosov, the Russian decipherer of Mayan, proposed that it was in fact phonetic writing, Eric Thompson just claimed it to be Bolshevik bullshit. So there could be a lot of what do you call bias which comes in when you kind of say that is this something writing or is this not? And so one of the things we try to do is basically come up with relatively objective measures to see whether something qualifies as writing or not. So how do we go about it? So if you ask what is writing, I mean, the usual way people define writing is that it's a way of communicating by some visible marks which has been standardized by some kind of convention. And what are you communicating? This is typically language. So what defines language? The usual definition is that it's a way of syntactic communication. And what is syntax? Syntax is essentially a way in which you put symbols in some very structured form. So typically, you have several words or several letters, and you put them next to each other to construct a meaningful segment. But it's not just any odd way that you bring them together. So there's also recursion. So you could have, like, for example, meaningful segments which themselves create another chunk which also carries a certain meaning, and then you put them in some kind of ordered sequence to create an even more meaningful statement and so on. So one way in which you could test piece of what you think could be writing, but what others are claiming is not writing, is to just look for syntactic structure. In other words, you're trying to look at evidence of compositionality, and you're looking for evidence of recursion. So why do we do this? Well, for all we know, all the known writing systems that we have evidence of actually have a mix of phonetic elements and logographic elements. And if it does have some phonetic element in it, it suggests that there would be some evidence of syntactic organization in those inscriptions. So this is a chart which is taken from Andrew Robinson's book, which kind of shows various writing systems in terms of how much logographic component versus how much phonographic component they have. And if you look at something like Finnish, for example, it's as close to a purely phonetic system as you can get. And then you have like the other alphabetic systems like French, English, and so on. As you go towards the right, which is you're moving towards more logographic component in the writing system, you have like systems like Japanese, which is a mixed system, which has some syllabic elements, but it is also the ideographic components because it has this Chinese characters. And then you have Chinese, which is not completely ideographic. It has some logosyllabic components. And then at the right, and this is of course not from Robinson's book, I put it there. If you think of the symbolic conventions that Dabbawalas at Mumbai use, it's also a way of communication. And it has a lot of logographic components simply because many of them are not able to read. And what they do is that they use a conventional system of signs which you think might be purely ideographic because they are not supposed to read and write, right? So, but surprisingly, you find that even in this system of sign usage, which is meant for use by people who can't read and write, you do have some phonetic components. So for example, the example I give, you see that over there it's written VLP, which stands for Vilepale, and EX stands for Express Building or Express Tower. So even in a sign system, which apparently should be purely logographic, I mean the symbol should simply convey some meaning independent of the sign usage because it shouldn't depend on what language you're trying to codify. There is some phonetic component. And so given that all known writing systems or all known communicating systems, I mean, arguably Dabbawala notation is not a real writing system, given that all such systems of written communication have some phonetic component, we are actually looking for some indication of this syntactic structure in those inscriptions. So Nisha has already fortunately given an introduction to the Indus writing system, and she has also mentioned segmentation, which makes my job easier. So what we are trying to do is that we are looking for evidence of syntax in a set of inscriptions by looking for evidence of recursion. So what is recursion? It means that do you have chunks of signs which are occurring very often together, which in turn you use to create meta chunks or super chunks of other signs which again occur very often and so on. And then you segment the whole sequence in terms of these motifs, where by motif I mean these chunks of sign which occur very often with next to each other. So what the argument over here is that if you can break the inscription into such chunks, and so here, for example, is a completely unstructured sequence of signs. All right, so phi 1, phi 2 up to phi 8 just stands for any sign. So if it's Indus sequence, these will be the various kinds of Indus signs. If it's a known language, it would be whatever alphabetic signs or ideograms that language is written in. So if you find that the clustering together of signs occurs in this form, so this is like a purely agglomeration kind of sequence where you just put one sign next to each other without any kind of a structural organization. They're just being added continuously from left to right. So this is basically an unstructured sequence. So if you build a tree like this, the tree height itself tells you that there is no structure. Whereas if you have a segmentation tree which looks like this, so for example, you find that phi 1 and phi 2 occurs very often close to each other. Phi 5 and phi 6 occurs very often close to each other. And then phi 5 and phi 6 occurs next to the compound made by phi 7 and phi 8. So this is a meaningful unit, this is another meaningful unit, and they together form another meaningful unit that very often occurs together, such that the segmentation tree you have has this very nice balanced binary tree-like structure. So the tree height, as you can see, it's much shorter than the tree height you get from this unstructured sign sequence. So this tells you that this has much more structured organization than this. And so what we're looking for is evidence of structured organization, which is shown on the right. So how do we go about doing this? So the simplest motif would be pairs of signs which occur very close to each other. And Nisha already mentioned this, that if you look at the distribution, the frequency distribution of the various Indus signs, then you find that it follows a Zipf's law. I mean, she mentioned Zipf-Mandelbrot. So Zipf's law is an even simpler distribution, which basically says that the frequency with which a sign occurs has this reciprocal relation with the frequency. So we know that there are certain signs which occur very often, like for example, a jar sign and so on. And what we're asking is, do pairs of sign occur together far more often than what you would expect from the individual occurrence frequency? So how do you find that? So, so this is the question. So we're saying that, okay, let's say sign I occurs with a frequency f of I. So let's say it occurs 200 times. Let's say sign j occurs with frequency fj, let's say 10 times. So how many times would you expect I and j to occur next to each other? So if it's occurring purely by chance, it would be, proportional to the product of fi and fj. All right? But if you find that the frequency of occurrence is much greater than that, you would know that, okay, something, has happening which is not purely by chance. So maybe there is some phonological reason or some syntactic reason that these two signs occur next to each other. How do you find how much greater the probability has to be before you say that this is not occurring by chance, but by design? Well, let me give you an analogy. So, especially the younger members of the audience would probably be very familiar with this, that among friends, there's often a lot of gossip that, hey, is individual A going out with individual B? Do they form a couple? Are they an item, right? But of course, as friends, any two individuals are likely to go out with each other occasionally, right? How do you know that, they're not just friends? Well, you say that, are they going out, are they being seen together more often than you'd expect by chance? Okay? So how do you figure out, how often they would be seen together just by chance? Well, you randomize. So for example, you can take a sequence like this, and here I'm taking an actual Indus sequence on top. And what I'm doing is I'm shuffling the signs. So if I shuffle the signs, what is happening is that I'm keeping the frequency of the individual signs still the same. But the frequency with which pairs occur is now completely scrambled up, right? So I can do one randomization, I can do another randomization, I can do yet another randomization, and this way I can create a whole ensemble of randomizations from which I can get some statistics about what's the probability that two signs would occur next to each other just by chance. And then I compare it with the actual probability that I'm computing from the empirical database. So given this information, I can try to segment it by first putting together signs, pairs, which have a much higher probability of occurring next to each other than simply by chance. So for example, here I'm looking at this particular seal from Harappa, and just by looking at the sign statistics, I know that this fish sign and these two vertical signs occur very often next to each other than one would expect by chance. So this has this highest abnormal frequency of co-occurrence. So I cluster them together, and then I come to this one. So this is a sign, for example, that Andreas was mentioning today in his talk. So this sign, along with this, like square with a vertical sign next to it, occurs with very high probability. So I'd cluster them together. And then, I find that, well, the two vertical sign and this kind of slight curve sign occur with very high probability. So in this way, I can cluster them together and gradually build up the whole segmentation tree. Now, you might say that, okay, why only pairs? There could be correlations which are longer than a pair. What about triplets? What about quadruplets? And so on. Yes, you can do that. And so once you start doing that, you actually can create a very systematic algorithm by which you don't actually just stop at 2. You systematically go through 3, 4, 5, 6 until you cover the entire sequence. And in this way, you get a comprehensive segmentation using science statistics of the Indus inscription. So let me give an example. And since this method should work on known writing systems, what I will show you is an example using an English word. So let me take a long English word like development. So using the technique that I just mentioned, you would find that VE occurs next to each other with the most abnormally high probability. So VE is combined together. Next comes ME. Next, it turns that ME itself forms a chunk which occurs very often next to N. And then this MEN forms a chunk which occurs very often next to T. So MENT is occurring as a chunk much more often than the corpus of English words than you would expect them to happen simply by chance if MENT or ME was occurring next to NT and so on. So you can carry out this operation until you have done this for the entire sequence, and then you ask which parts of this sequence tree have higher than random probability of occurrence, and this allows you to put dividers into the segmentation tree, so you can separate it out into de, ver, lup, ment, which exactly corresponds to the phonological building blocks of this particular word. So this is just to validate that this method works with known writing systems. So you can see how the segmentation tree of the English words that you have created out of this technique shows that these tree heights are actually much less than what you would expect from the randomized. You can take those same English words, randomize them, and you can try to construct trees out of them. And you can see that those are much closer to completely unstructured sequences as you would expect compared to the actual empirical trees. So you can do this across different corpora. So for example, you can do it for Sanskrit, Tamil, Chinese, Urdu, Sumerian cuneiform. And of course, you can do it with Indus. And interestingly, you find very similar organization across all of this, which suggests that Indus might actually have a very strong phonetic component. It's not just counting tablets, or it's definitely not just religious symbols just strung together without any order. Another interesting thing you can do is that you can look at what are the significant subsequences. So for English, for example, you find that this significant subsequences actually correspond to very commonly occurring prefixes, suffixes, very common endings like Asian. Lots of English words end with et, Asian, ant, and so on. So you can construct a similar kernel lexicon of significantly co-occurring signs that can help in doing a sequence alignment of Indus sequences. And actually, this can actually help you to identify, for example, allographs. I don't have time to go into this, so just mentioning that this is one of the advantages of doing this kind of a technique. And you can look at the Zipf's law for the significantly occurring subsequences, and you find that for English, for example, they exactly follow a Zipf's law. This is surprising because we are looking at words. Zipf's law normally applies to sentences. So we are looking at the letters of a word. So if you just looked at the English letters, it will not even follow Zipf's law. It will follow exponential. But if you do this over the significantly occurring subsequences, you find that it exactly follows Zipf's law with an exponent of 1. You can do the same thing with Indus. So for Indus, with the signs itself, as Nisha pointed out, it follows an approximate Zipf's law. But now if you look at the frequency distribution of the significant subsequences, you find that it's much closer to normal Zipf's law with an exponent very close to 1. I'd like to end with this particular slide because this is pointing to a very universal pattern of how words of any language are actually constructed out of these motifs that we find from this method. So normally, different writing systems, different languages have words of very different lengths. So for example, Korean would be quite short. The words essentially typically consist of 2 or 3 graphemes. And that's because each of these symbols in Korean is actually a composite. On the other hand, if you look at something like Hawaiian, the average length of word is like 10 characters. And that's because it's mostly composed of vowels. Consonants are actually fairly low in number. So you'd say, okay, so word lengths can actually vary a lot. But if you now look at how many significant motifs does each word can be broken down into, you find that surprisingly, across all of these writing systems and languages, they can be broken down into just 3 motifs, typically. Right? They can vary between 2 and 5 and so on, but the average number of motifs is 3. Okay? So it tells you about something universal about words. Words essentially are composed of, on average, about 3 significantly occurring subsequences, three motifs. And Indus, you can see, is right there. Okay? So all of this leads us to the conclusion that definitely there is a strong phonological component in Indus. It's not as logographic as some people would claim. And I'd like to end by thanking my collaborators, Ashraf, who of course already has spoken, Raj, who was my first PhD student and also was instrumental in getting us started on the segmentation work on Indus, C. Subramanian, who is based in Chennai, who has helped us a lot with gathering the databases, and certainly Brian Wells, who when he was a postdoc at our institute, actually started organizing this database in the computer, and that's how we had access to this extensive database, which has helped us do most of this work. I'd like to acknowledge generous funding from the Department of Atomic Energy, which has recently helped us set up the IMSc Computational Epigraphy Lab. And since there are lots of students here, I'd like to say that we are very much looking for postdocs and project research assistants to employ in the various projects of this lab. So if you're interested, please do write to us. All right, and thank you for your attention.